Hi, welcome to our last video lecture on using physics and computer code to simulate projectile motion. In this lecture we are going to finish up our code, and you should be able to run your code to predict how far your projectile is going to go and then compare that to experiments that you might come up with. So here's where we are. We're on the last of our video series, simulating projectile motion using computer code. In video 5, if you remember, we set up this nice simulation where we could launch a projectile with an x velocity and predict how far it would go. We're going to add a little bit of complexity to it, and that is going to be, what do we do with a changing launch angle? So what we're going to do is, if here is our x position and here is our y position, previously we would have been launching a projectile from some fixed height at a fixed x velocity and seeing how far it would go. What we want to do, because we'll probably be launching our projectiles from the ground and at different launch angles, is we want to launch it from here and see how far it will go. So one of the tricks there is that we may know what our projectile launcher's velocity is, but we need to figure out how do we break that velocity down between an x velocity and a y velocity. So I'm going to teach you how to do that, and it's going to involve trigonometry. And so if you, in these video lectures, we're using a lot of these math skills that you probably thought you would never use. We're going to use algebra, trigonometry, geometry. So what we want to do, we want to take our, so you can actually take a velocity, and depending on the angle, you can break that velocity down into its different components. The y velocity, which is going up and down, and the x velocity, which is going left to right. So let's think about this arrow, which is called a vector, as our velocity. So we want to take that and break it up into the x velocity and the y velocity. So we're going to use, we're going to try and measure the angle. So when I've done this experiment before, I've used, this is my son, who we did this as a science fair project together. We used this Nerf gun launcher, and then we taped a protractor with this string dangling from it and this key as a weight, and we would use this to measure our launch angle. So the way this is set up is that if you held this gun horizontally, that key would hang down here. That's at about 90 degrees. So we were measuring the angular distance from vertical. So if you were launching it straight up in the air, you would have a launch angle of 0. And if you were launching it perfectly horizontally, that would be a launch angle of 90 degrees. So we want to measure how far we are from vertical. We want to measure this angle here. So I'm going to give you a little mnemonic device that I remember since my trigonometry days. This is this word SOHCAHTOA, and what this means is the sine of an angle is equal to the opposite distance divided by the hypotenuse. The cosine is the adjacent divided by the hypotenuse, and then the tangent is the opposite divided by the adjacent. So let's figure out what that means. So if we were looking at this launch angle, so our distance from vertical, again, if this were 0, that means our y velocity would just be equal to the velocity. So what we want to do is we want to say the sine of our launch angle, we'll call that theta, is equal to opposite over hypotenuse. In this case, the opposite angle here, so the opposite vector from our angle is going to be the x velocity. So we can say the sine of our launch angle is going to be equal to the opposite over hypotenuse, so that's x velocity over the hypotenuse, which is represented by just the total velocity. It's okay if this doesn't all sink in. Hopefully it will as you start coding. So we're going to assume that our Nerf launcher, we know from maybe the manufacturer specifications what the velocity is coming out of this gun. We just don't know how much of that is x velocity versus y velocity. So if we know the angle and we know the velocity, we can solve for the x velocity. So if we do some algebra now, we can solve this, rearrange that equation, and we get that the x velocity is equal to the measured velocity multiplied by the sine of theta. Similarly, if we look at this second part, the part, the cosine of the angle is equal to the adjacent over the hypotenuse. So if we look at our angle here, adjacent to that is the y velocity. So if we do the same thing, we get the cosine of theta is equal to the y velocity divided by the velocity. And we solve that, we get that the y velocity is equal to the measured velocity from the manufacturer multiplied by the cosine of theta. Okay, so you probably thought you'd never have to deal with trigonometry in your life. All this math that you're learning in school becomes really valuable, and actually throughout these activities we're doing, we're using calculus, although we haven't really talked about it like that. We're using algebra, we're using trigonometry and geometry, so all this stuff really becomes useful, especially if you go into STEM and particularly engineering. Okay, so there's our launcher. So now we're going to go back to our code. We're going to try and remember these equations, the x velocity equation and the y velocity equation. And then we're going to go back to our code that we've developed by launching Google Chrome. So here I'm going to go to scratch.mit.edu. Here's my code if you remember. So from before, you remember if we could launch this, our projectile, at a particular velocity, but we only gave it an x velocity. So now we're going to modify our code so that it can deal with a changing launch angle. So what I'm going to do first is I'm going to grab this repeat loop and I'm just going to disconnect it so that this part doesn't run. We are going to define some new variables. So let's go here to variables. I'm going to define this angle, which is launch angle, and I'm also going to define this VEL, which is our velocity. So now what I want to do is I want to define my launch angle and my overall velocity, and then I want to use those to calculate my x velocity and my y velocity. So first, I'm going to go here to set my launch angle. We'll just keep it set at 0, that's fine. And then I'm going to do another command like that. I'm going to set the velocity. So we're just going to define these manually. A launch angle of 0, which would mean you're shooting the projectile straight up in the air. Let's give it a velocity of 70 meters per second. Okay, so now what we want to do is we want to change our x velocity. We want to calculate it instead of just picking a velocity like we did before. We want to calculate it based on our overall velocity and our launch angle. So what I'm going to do is I'm going to use a formula. Remember that x velocity is equal to the velocity times the sine of our launch angle. So I'm going to use this multiplication operator. I'm going to put that here, and then I'm going to use this other operator. We can actually use like custom functions down here. I'm going to put that in, and I'm going to get the sine function. Go back to my variables. So here I want to put in velocity in this first part, and then I want to put my launch angle in this second part. So there, now we set the angle and we set the total velocity, and then this formula will calculate how much of that total velocity is x velocity. So it's going to be x velocity equals the velocity multiplied by the sine of my launch angle. We want to do something similar for the y velocity. I'm just going to hover over this green part and duplicate it and stick that in here. But the y velocity now is the cosine of my launch angle. Okay, so now I have basically the same code, except now instead of giving it an x velocity and a y velocity, now I give it a launch angle and a total velocity and let my code calculate x velocity and y velocity. I'll put things back together here. I'm going to move these guys to kind of get out of the way. All right, so I'm going to erase my previous line. The other thing we want to do is we want to be launching our ball from ground height. So previously we said the ground was at a y position of minus 150. So I'm going to start my initial launch point at minus 150 in terms of y. So it's going to start from about right here, same starting x position. So I'm not connecting my code yet because I just want to make sure that this actually works. So if I give this a launch angle of 0 and a velocity of 70, let's make sure that my x and y velocities are calculated appropriately. And actually, let's see. Yeah, so they're here still. So I'm going to click go. Okay, so let's see what happened. So I did set my launch velocity to be 70 and my launch angle to be 0. So when my launch angle is 0, that means I'm launching the ball 0 degrees from vertical. I'm launching it straight up. So when we do that, we see that our y velocity becomes 70, which is perfect. That's just what it should be, right? We're launching it straight up. So all of our velocity is going in the vertical direction, and then none of our velocity is going in the x direction. Let's try it again. Let's try setting a launch angle of 45. So 45 is halfway between 0 and 90, so this should give us equal components of x velocity and y velocity. Let's make sure it does that. So I click there, so it takes my 70 and it says, okay, well, if I had a launch angle of 45 with a launch velocity of 70, that's going to break it up into 2 equal parts, x and y, each at 49.5 meters per second. So that looks good. So we're just kind of checking to make sure our code makes sense. If I give this a launch angle of 90, that means we're launching it directly horizontal, so we should see our x velocity is 70, so all of our velocity is x velocity, and our y velocity is 0, so that makes a lot of sense. Okay, so now, if we reconnect this code, it's going to be launching our projectile here from the bottom left, and now it's actually going to launch and go at this particular launch angle and velocity. So let's go back to, let's launch it directly vertical with a launch angle of 0, and let's see what happens. So think what you think will happen. Okay, here we go. Okay, so we launch it straight up, and then it comes straight down, so our ball doesn't really go anywhere. It just goes up and then back down, so that is great. Okay, now let's give it a launch angle of 10 degrees, and see what happens. So when we launch it at 10 degrees, okay, so it gives us, we get a new y position and x position from that. Great. Let's go back to our code. Let's give it 20 degrees, and we'll come back here, simulate it, and you see we can read all of our acceleration, our velocities, and our positions all in real time as the ball travels through the air. So that launch angle of 20 results in this greater distance. Okay, 30. I'll just do a few of these so you get the idea. So what's cool is that we've written all this code from scratch, and no pun intended, but we're doing this in a computer language called Scratch. So pretty cool the way that you can use physics and some reasonably simple computer code to try and make predictions about what's going to happen physically in the world. Okay, so you can see how we can now collect a bunch of measurements. So what I would recommend here is you want to try and get a really good estimate for what your actual launch velocity is. So if you're using a Nerf gun, for example, you might try and look at the manufacturer's specifications to try and see that launch velocity. You may try and do something like get a stopwatch and try and measure a distance and see how long it takes to go that distance, and then calculate the velocity manually like that. We want to try and do our very best at measuring this launch angle using something like this inclinometer here. So you want to be very careful that you're launching it at the correct angle, and then your inclinometer is on there straight and everything. The other big variable here that we don't really know exactly is this drag coefficient. So my recommendation is you could run an experiment. You can actually go shoot your projectile, measure a bunch of distances, collect that data in a spreadsheet or something, and then you could go and run your simulation, and you can see how well does your simulation match up with the data you've collected. If your simulation predicts that the ball goes a lot further than you saw in reality, you could increase this drag coefficient, which would cause the ball to go less far in your simulation, and you could do some trial and error and adjust your drag coefficient in your simulation until you get results that make your simulation match up with reality. Anyway, that's it for these video lectures. So now you should be experts at using Newton's laws of motion as well as the physical governing equations that go with it. We've used trigonometry and algebra, and really what we're doing is calculus at the end of the day. We're just solving differential equations numerically, and you don't have to remember that, but once you get along in your schooling and get into calculus, you can look back and remember that you've actually done some of this back when you did this science project.